Today we will discuss magnetic force on current carrying conductor. In the previous class we have discussed Lorentz force, the force that exists when the current is moving, when the charge is moving, and we have discussed and how it can be calculated. At the same time we got the idea about the direction of the Lorentz force. In the next lecture we have also discuss in detail the various possible applications of Lorentz. Today, in this lecture, we are moving further to understand the basics about a wire, a conducting wire in which the electrons are moving, the charge is moving. And we will discuss what effect the magnetic field can impose on such wires and what is the significance of this. In this lecture, first we will discuss introduction about this topic. Then we will discuss how a wire can be placed in magnetic field, and if a wire is placed in the magnetic field, what will be the force, how the mathematical expression can be obtained from this, and other details. At the end of this lecture, we will be able to learn the various effects of magnetic force on current carrying conductor, and we will able to calculate the magnetic force on current carrying conductor. When we talk about current carrying conductor, then first we should know the meaning of current carrying conductor. First thing is conductor. Conductor which conduct electricity, from which electron can pass. Those are called conductors. We have also discussed in the same unit about non-conductors or dielectrics, from which the current can't pass. But if you can pass the current with then it's called conductor, and we have many applications of these conductors. Now, current carrying conductor means a conductor in which you are passing the current by applying some a battery or some voltage. You are passing the current from a conductor. As a matter of fact, there are many examples of current carrying conductor. All the domestic wiring in your home is an example of current carrying conductor. Whenever you switch on, current carries to your conductor. We have a network of current carrying conductor in our home. Copper, basically. Copper and aluminum are the two basic conductors. So whenever we have current carrying conductor and we place this current carrying conductor in magnetic field, now something different happens. Different in the case of if you are having only charge particle, as we have discussed in the class on Lorentz force. Suppose you are having only charge particle and you apply magnetic field, then the particle may move from one here to there. But in the case of current carrying conductor, the charges ordinarily can't escape the conductor. The charge is passing through the conductor. So the magnetic force on the charge moving in a conductor is transmitted to the conductor itself. So there is a difference here. Before going into detail, see this figure. In this figure, we have designed two magnetic poles, N and S. It is shown here. This is your north pole and this is your south pole. These two are the north and south pole here. And there is a gap between north pole and south pole. This is shown here. I am showing here by this. Now we place a wire, a current carrying wire in between this. I am denoting with this wire by this line. In this wire there is a battery is applied here. Due to this, current passes through this wire. Now whenever we have magnetic field here, magnetic field move from north to south, so magnetic field exert a force. And this force on current carrying wire. Now I am discussing here that magnetic field is exerting a force and magnetic field is in direction of from left to right here. And the current is moving in upward side. Now the force, if you want to calculate force on this current carrying, then it can be calculated using right hand rule. The right rule, obviously the right hand rule is same as we have discussed for individual moving charges. This force can easily be large enough to move the wire, since typical current consists of very large number of moving charges. So the current, if it is current is there in the upward direction and the magnetic field from left to right, then there will be a force in upward direction using right hand rule. We can derive an expression for magnetic force on a current. As we have seen in the last figure, the current carrying conductor is placed in the magnetic field. Then the force will be there. As we have discussed in the last lecture, the magnetic field effect on a single charge, and here we are discussing the magnetic field effect on a stream of charge current. Then here we must realize that the effect of magnetic field on an individual charge can be taken as a sum. Here we can take the sum of magnetic force on individual charges, as the force is ultimately on the individual charge and we are using here a series of charge. All the force will add because all the force are moving in the same direction. So first we will calculate, we will take the initial values from magnetic field on individual charge, then we will move to add all. Suppose a force on individual charge that is moving with the velocity of Vd, drift velocity, the force can be done as qvb sine theta. This value is given by Lorentz force. F is equal to QE plus V cross B. And so V cross B can be done as VV sine theta. Here VD is the drift velocity of the particle. The velocity due to electric field, that is called drift velocity. Here we use the word drift. Is to remember this word, you must know there are two types of velocities, drift velocity and diffusion velocity. We use two words, drift and diffusion. The charged particle can move from one place to another place, and the charged particle motion is depend on two methods, two circumstances. Whenever we are using the word drift velocity, it means the velocity or the motion is due to electric field, application of electric field. If we are using any field, electric or magnetic field, to pass, then it is called drift. Drift is possible only by application of external field, that is electric field. So whenever we have such type of application of electric field, then the motion is called, the velocity due to this field is called drift. But another is also there, that is called diffusion field velocity, in which the charge move from one place to another by concentration gradient. It means at one place the concentration is high, at another place concentration is low, then the charge move from higher concentration to low concentration, and the field in this case is called diffusion, and the velocity is called diffusion velocity. The velocity occurs due to change in concentration. But in the case of drift, there is no such case. Whether charges are higher or low, it only moves due to electric field. So whenever we apply force on individual charges, magnetic force, then the force is given by qvb sine theta. Here I am talking about single charge, individual charge. Now we will add it to get for charge for multiple charges, force for multiple charges. If we take B, magnetic field B is uniform over a length of wire, and the current is moving through the wire, and magnetic field is such that it is uniform everywhere in the wire, throughout the wire, and zero elsewhere, everywhere elsewhere it is zero, then the total magnetic field on the wire can be written as F is equal to QVB sine theta n. Yes, here n we used n, that n is number of charge carriers in the section of wire of length L. If total charge carriers are capital N, then the field is this much. So simply we have just calculated for 1, and we have extended this idea for N, provided the field is uniform. Here capital N is basically the number of charge carriers, and if you are having you are defining another term, that is n small n, and n is the number of charge carrier per unit volume and v is the volume, then this can be written as like this. Here v is the volume of the material, and v, the volume, can be written as A into L. L is the length of the wire and A is the area. If A is the area, here in the case of our case we are discussing wire, so A will be a cross-section area of the wire and L is the length of the wire. Then the force can be written as by putting by replacing capital N by first and small n into V, or and V can be converted to A into L. So can be written as F total force is equal to QVB sine theta NAL, where N is the number density and A is the area and N is the length. So for the current carrying wire, the force can be written as NQAVD IB sine theta. This can be written as we have used N the charge density, A is the area and L is the length of wire. Now we know that if the current is passing through any wire and the diff velocity is Vd, then the current can be done as NEA NQAVD, where Vd is the drift velocity, I is the current, A is the area, Q is the charge, and is the number density. If we put this value there, and we use this here, then this will be converted as this F is equal to ILB sine theta. So in current carrying wire, the force is ILB sine theta. If the force is ILB sine theta, this is the equation for magnetic force on a length of wire, L of wire. carrying a current I in a uniform magnetic field. Now, if we divide both sides by L, we can calculate magnetic force per unit length. Magnetic force per unit length in wire, as we are saying we are using length wire, then we can calculate this, and this V is equal to IV sin theta, which is called magnetic force per unit length. Here what we did, we have just converted the magnetic force that we have discussed from the Lorentz for, we have just extended for wire in place of single charge. The direction of this force is given by right hand rule, as we have discussed in the previous class. With the thumb in the direction of current I, then the fingers in the direction of B, and perpendicular to the palm points in the direction of F. Right hand rule says that you just stretch your right hand palm, and in this case, if the thumb is showing the current direction, fingers are showing the magnetic field direction, the perpendicular to the drawn on the palm gives you the direction of force on the wire. It is shown here also. This is the direction of current. This is the direction of magnetic field, and perpendicular to both the direction of force. The force here is perpendicular to both I and B. Magnetic force on current carrying conductor is used to convert electric energy to work, and motors are the prime example of this. This is the application part of this force. Magnetohydrodynamics is the technical name given to a clever application where electromagnetic force pump fluid without moving the mechanical part, just by application of in the particular direction of magnetic field. So these are the few examples or few applications of this magnetic force that we have discussed in the previous lectures. Here we have shown here magnetohydrodynamic example. The magnetic force on the current passed through this fluid can be used to pump something. The force is always there. We are placing a wire in the magnetic field, and I is in perpendicular direction, magnetic field is other direction, so it will move the fluid through this pump. This is an application part of this. Here, a MHD propulsion system is shown. It is a nuclear submarine. This could produce significantly less turbulence than propeller and allow it to run more silently. The development of a silent drive submarine was dramatized in the book and the film The Hunt for Red October. Here we move the particle as we have shown here. We apply a magnetic flux in a one direction and electricity another, and so the liquid move easily. A strong magnetic field is applied across a tube and current is passed through the fluid at right angle to the field. This results in a force on the fluid parallel to the tube axis as shown there. The absence of moving parts makes this attractive for moving a hot chemically active substance such as liquid sodium employed in some reactors. Experimental artificial hearts are testing with this technique for pumping blood, perhaps circumventing the adverse effect of mechanical pumps. Cell membrane, however, are affected by large field needed in MHD, delaying in practical application in human. MHD propulsion for nuclear submarines has been proposed because it could be considerably quieter than conventional propeller drives. So these are the few examples that can be used for current carrying wire. Thank you. In this section, we have studied magnetic force on a current carrying wire. We have studied expression and finally the application of this force in MHD and the silent flow of fluids. Thank you.